lecture is really the lecture that we've been building to for some time. We've talked about the basic principles of quantum mechanics and relativity, and how putting them together really constrained the way that possible theories could be. And we found, in fact, that our world behaves just like we would expect from these principles. Of course, there's aspects that aren't determined. So the number of different types of particles and the number of different types of forces are something that we have to go out and measure and see how it is in our world. But we've now done that, and it fits to this quantum field theory, okay, that was expected, and it's remarkably successful, right? It's remarkably successful both sort of from a qualitative point of view, in that we really understand all of the different forces that we see are really aspects of the same underlying structure, and it's also very successful quantitatively. So there's particular things that the theory is able to predict very accurately that we're also able to measure very accurately, and every time that's happened, we've seen that these agree to astonishing levels. So in some cases, to 11 decimal places. It has also made very clear predictions of phenomena that we hadn't observed yet and that we should observe, and we'll see an example of that here, that were then confirmed by the theory. And so everything looked great except from this basic fact that the theory can't accommodate particles that have mass. And a basic thing that we know about the universe is that, or our world, is that things have mass. And so that was a very confusing, that's very confusing, right? And there's a way out of it that looks sort of ad hoc. You add this new field that has a particular form of the energy, and it looks like you're putting in something to just solve this one problem. And in fact, that's really what people were doing, except that there's a very residual effect from doing this. There's this Higgs boson that is something that hadn't been observed yet. That is predicted if this concept of adding this Higgs field is true. So that's what we're going to talk about today. And then last week we talked about ways that we can test this whole picture. Okay, and that was in proton collision. So we can really calculate, the theory can calculate what we should see when we collide protons. And we have a whole experimental program to do this. Okay, we have. And we talked about this, how we have these very big detectors that you can sort of think of as cameras. They take pictures that are a little more complicated than regular pictures. They have these four basic outputs, okay? And by correlating the outputs that you see within the detector, we can reconstruct the basic particles that we're interested in. Okay, and this is what we talked about a lot last week. And of course, there's really a lot of detail in developing these images. And also, there's challenges associated with taking the pictures at a quick enough rate. And that's this whole issue of triggering or deciding which pictures to keep. And then there's also subtleties in how you deal with these, and how you actually process or develop these images. Okay, but these are the basic tools that we'll use to look for the Higgs boson. And then I think 2 weeks ago we talked about the Higgs boson itself. So this is this residual piece that this Higgs field predicts that we should observe. Okay, and so it's a new particle, and we actually know an awful lot about this new particle. So it's not like the theory is saying, oh yeah, there should be this new particle. It's really making a very sharp statement about what the particle should be. Okay, in fact, all of its couplings are fixed, so it should couple to matter according to the mass. So the probability for an interaction with matter particles should be related to the mass of the particles that it's coupling to, and it can also couple to massive bosons, so W and the Z. And then we know a lot about its spin as well. There's only a few possibilities that it could be, and it's strongly favoring the spin 0 scenario. And so really the only thing that we didn't know that's not predicted is the mass of the Higgs. Okay? Now there was a related issue to the mass, and that's the fact that if you scatter these massive W's and Z's, the theory stops making sense. You start to get probabilities that are bigger than 1, so it's really signaling a breakdown of the theory. And this can be solved by exactly this Higgs boson. Okay, and this needs to happen comes in about 1,000 GeV or a TeV. And so that is some sort of a loose prediction that's given by the theory that the theory will break down at a TeV. So this Higgs boson should be less than a TeV, but other than that, the mass is really the only thing that's not specified. Now, if this was a longer lecture series, I would have gone into the fact that a lot of people are unhappy with this basic picture. Okay, it's putting in this Higgs field. It's not very elegant, as I've alluded to, and it gives you a spin zero particle. And I'll talk about this next week. There's problems with spin zero particles. And so there were a lot of people before the LHC turned on that were really advocating different approaches to solving this problem. Okay, the problem of masses. And all of these theories, they were very different in detail, but they all had something that would fix the fact that that these W and Z scatterings become badly behaved at high energy. So that's really something that's not particular to this Higgs field that we put in, but it's a generic in all possible theories. It's really just about quantum mechanics and relativity. If you have these massive W and Z bosons, those probabilities cease to make sense. And so, despite the fact that there were proposals for different theories that weren't this condensate that I talked about, they all had new effects that would come in that would fix this W and Z behavior at about a TeV. So that was something that was really sort of independently, if you like, known apart from the Higgs boson. But nonetheless, this Higgs boson approach is really the simplest way. You put in this one theory, or this one field, this decondensate, and that gives you this boson that has all these nice predictions. Okay, and so today's lecture is going to talk about how we actually discovered the Higgs boson, and then I'll spend more time talking about what do we know now about it, so since the discovery, what's sort of been the program to study it, and what are things that we don't know about it. Okay, so the first thing to ask is how are we going to make Higgs boson? So of course we do this by colliding protons, that's the whole point. And we know from last week that it's really quarks and gluons that are colliding, the things within the proton. And so this is a picture that we saw last week. This shows the probability for either a quark or a gluon to collide in the proton as a function of the fraction of the energy that the proton, that this particle carries. So most of the time, if you're at high fractions of proton energy, it's two up quarks and a down quark. You see that reflected here. The output's sort of twice as big as the down, and these things are the dominant probabilities. And at lower fraction of the proton energies, it's really this gluon piece that matters. Okay, so it's really, you think that these energies were colliding gluons, not really protons or quarks. Right. So that's what I want to say.
Question. How come we're smashing protons together to find bosons which do not exist inside the proton?
Yeah, I'll talk about that. I'll talk about the next two slides. Okay, so but now for the Higgs, we know the interactions, right? So we know that it has to couple, to produce a Higgs, we have to have a coupling to matter like this. Okay, these W's and Z's are not within the proton. So we're looking for some interactions like this. Now the problem is these things that have high probabilities, the gluon and the up and down quark within the proton have small masses. Okay, so so here the gluon has no mass actually, and the up and down quark are shown here. This is a distribution that shows the mass of all the particles in the standard model. And so these things are really light. Okay, and this is a problem because the probability for this thing to happen depends on this mass. Right, and so basically all things that exist in the proton are relatively light. That means there's a small coupling to the Higgs. So there's a small probability to produce a Higgs from these light things. Okay, so really what we'd want to do is we'd want to get some of these guys, right? We want to get a top quark that's like 100 times heavier than the proton, or the W and Z are also similar masses. These things have high probabilities. This number would be very big. So these are the heaviest guys in the theory, and this would be our best chance of making it. Okay, so we really want to use these types of diagrams, where this is the top quark and this is the W and the Z. Now the problem is these things don't exist in the proton, right? And we don't have top and WZ colliders. Okay, so what we have to do is first make these guys and then have them interact to make the Higgs. Okay, so these guys, so the top and the W and the Z, those do couple to things within the proton. So the idea is to have really a two-step process. First we create these guys from things within the proton, and then those guys then create Higgs. And so I'll show examples of that. Here, there's the main way we do this is with a diagram that's called gluon fusion. And the idea here is that you have these gluons that are very abundant within the protons. They can interact with a top quark. Okay? So you can get this, a loop of top particles. So basically, this gluon can go to two tops. One of the tops kills the top from the other gluon, and now you have two tops lying around, and these can interact and make a Higgs. Okay, now this has a very high probability of happening from this coupling. Of course, as we saw in an earlier lecture, this is a higher order diagram where it has a smaller probability for happening because it has this loop within it. So there's this loop factor that we talked about, and there's also more of these vertices. Okay, so instead of just having a simple vertex like this, you now have three vertex, and there's small numbers associated with those, or relatively small numbers associated with those vertices. Okay, so this is really the leading layer, the most probable way to produce a Higgs. Another way is called a vector boson fusion. Okay, or I'll probably say VBF here. That's what I mean by this. This is relying on this sort of diagram. So the idea here is instead of using quarks, or instead of using gluons, we use quarks that are also within the proton. These things can create W's and Z's. And so the idea is you have a process like this where one quark comes along, spits off a W, and another quark comes along and spits off a W. Now you have two of these W's lying around. They can interact and produce a Higgs with relatively high probability, okay, because of the high mass here. Now again, this is also a more complicated diagram than the simple this simple stick figure. So you have other vertices here that come in with smaller, that reduce the total probability for this to happen. So this is the dominant one, and this is the next leading. Okay, but this is really why the Higgs was so hard to find, right? It's not because the Higgs is really massive, as we'll see. It's because the Higgs couples very weakly to particles we have lying around. So the things that we can collide are things that are stable, right? Things like protons. But those are stable because they have light masses, and so it's really, it's almost a catch-22. The things that we can't collide don't interact strongly with the Higgs. So the idea is here we first need to create a pair of unstable massive particles, and then these, as a second order process, interact with the Higgs. So this is really why the Higgs was so much harder to find than other particles that have relatively similar masses that were seen before. Okay, so that's how we're going to produce the Higgs. Now the question is where to look for the Higgs. I said earlier that we had this loose indication that the Higgs must be less than 1,000 GeV or a TeV. That was just coming from the basic consistency of the theory. But as I mentioned last lecture, we also had constraints coming from these loop type diagrams here. Okay, so these are diagrams that would contribute to the mass of the measured mass of the W boson, or the mass of the mass of the top quark. So these things have been observed, almost 10 years ago, longer in some cases, and they've been studied. Right? So we've studied the mass of them very well, and we could potentially detect effects from the Higgs in diagrams that look like this. Okay, and in fact, by doing this, if the Higgs was a TeV, we would expect a very big contribution from diagrams that look like this. Now, when we measured these masses, there was no contribution that was found. So it looked like the Higgs didn't have a big effect. And so that allowed us to put much tighter limits on what the Higgs mass could be. So from studying these things, the Higgs mass was predicted to be between 50 GeV and 150 GeV. So another way of saying that, if the Higgs was in this region, it would not contribute significantly to these diagrams in a way that we'd be able to see. So now we have an even sharper prediction for where the Higgs mass should be. This isn't coming directly from theory, it's coming from theory and the measurements of these W and top quark. And in fact, we also had limits from direct measurement. So in particular, the experiment that was used to study the mass of this W quark was a precursor to the LHC, but it collided leptons, so an electron and an anti-electron. And it was also run in a mode where it would look for the Higgs. That was the main goal for this later in its lifetime. And so it searched for the Higgs in processes like this. You could collide two electron and anti-electron. That would make a Z, and now the Z has a very high coupling to the Higgs because that's massive. So it could spit off the Higgs, and you could look for it in this way. Again, nothing was seen, so we didn't see the Higgs in this mode, and this allowed us to set it up a limit, an even tighter limit. So it predicted that the Higgs, or it was telling us that the Higgs must be bigger than 115 GeV. Okay, if it was smaller than 115 GeV, it would have shown up in an earlier experiment. So now we have an even sharper prediction, right? It should be between sort of 115 GeV and 150. Okay, so that's sort of where we're looking for it. Now the big question is how to look for it. How do we, once we've produced it and once we know roughly what mass is, how do we actually, what sort of pictures do we look at? And so the thing to observe here is that the Higgs boson quickly decays to other particles. Okay, and the theory tells us which particles it should decay to. And in fact, it's these basic Higgs interactions that control how the Higgs decays. Okay, and the way that we talk about how the Higgs decays is in terms of branching ratios. And so that's basically how often the Higgs decays in a particular way. And I'll walk you through how this is done. So the theory predicts that a branching ratio for a particular particle, so let's say we're interested in W boson, say, is given by the number associated with this diagram, where it's the Higgs going to WW, divided by the sum of all the possible diagrams. Okay, so if, the way to think about that, if all these diagrams add up to a certain number, so all the ways the Higgs can decay, and the W is half of that, right? Half of that number, then the branching ratio would be 50%, or half the time the Higgs would decay to the W's. So it's really these basic interactions that are controlling how often the Higgs decays in a particular way. And the thing to point out is all of these have mass, right? So these interactions are all proportional to mass. And so you can do these calculations in the theory very precisely, but the bottom line is the Higgs wants to really decay to the heaviest particle around, provided that it has enough energy to do it. Okay, so of course the particle that it's decaying to has to be less than half the Higgs mass just to conserve energy. And so if you do the calculation, here's what you get. So there's it depends on the Higgs mass, okay, a bit, but we know the region we're interested in now is sort of this 115 to 150. So in this region, this is the branching ratio, or how often it decays in a particular way. And so you can see, let's say at 120, it decays almost all the time to pairs of bottom quarks. So that's the highest. This is basically the most massive thing it can decay to. It doesn't have enough mass to decay to the WW with this energy. There is some significant probability to do that, but it's more of a quantum effect. It's not decaying directly to W's that have the W mass. So it decays to B's here like 60% of the time. It also can decay to tau quarks or tau leptons. This is another massive particle that has a relatively high branching ratio. So that's about less than 10% of the time it does that. This is C is another form of quarks. You can see there's also there's Z pairs of Z's. So again, it's much smaller than the BB because these have to be. It doesn't have enough energy to do this, so it has to do it via a quantum mechanical way. So it can decay to ZZ. And you also know that it can decay to gluons, okay, and to photons with at some probability. Now this may seem strange at first because these things don't have mass. But in fact, they can do this through loops. So just the way that we produced it was through this loop of top quarks. So to produce it, we clogged these gluons, made a loop of top quarks, and we produced the Higgs. You can also get the same reaction going the other way. So if you have a Higgs, it can decay to a pair of top quarks, and there's some probability for that to then make this triangle diagram and decay to gluons, or you can do the same thing again to photons. Okay, so you can see that even though these things have no mass, or they have no direct coupling to the Higgs, you can get an effective coupling through these loop diagrams. Okay, and you can see but it's actually pretty small. So for photons, it's like it's sort of less than 1%. Okay, so here's all the ways that the Higgs can decay in terms of our pictures that we talked about. So the biggest one, and so let's just go through these and see which of these are viable. So the first one is these jets. So this is decaying to these sprays of particles that have tracks associated with clusters in both calorimeters. So this is totally hopeless. So the Higgs decays this way about 10% of the time. these events we can't even trigger on them. So these happen at such a high rate, or there's background events that look just like this that happen at such a high rate that we can't save all of these events to tape or to disk. So this is hopeless. So now the biggest one is 60% of the time it decays to Bs. They look very, very similar to these, except they have this displacement that we talked about last week. This is actually also hopeless. There's way too much background. So you can produce Bs directly from gluons, and it turns out that totally dominates. We could probably trigger on it if we wanted to, but even if we could save the events, there would be way too much background to see any Higgs signal. So now another one we can think of it is this Higgs to tau decays. So this is also hopeless. Okay, in gluon, at least in the gluon, the dominant gluon fusion diagram. The VBF is hard. It is doable. We'll come back to this, but it's not used in the discovery. It doesn't have enough sensitivity to see in the discovery. So we're really left with these three other ways to do it. So the searches, especially at first, really focused only on these three signatures. So I'll kind of walk through each of these in the next slides. Okay, so now we know where to look. We know how to produce it. We know what pictures to look at. Now a big question is how much data do we need to actually see it? Okay, so we'll sort of walk through an estimate of this by estimating how often we make a Higgs. Okay, and we'll start with a warm-up example, an easier one. That's how often do we make a W or a Z particle? Okay, and so we talked about this I think 3 lectures ago. So we have this cross-section, okay, this controls the probability to produce a certain process, and these can be calculated with these stick figure-like diagrams. Now this cross-section has units of area, okay, and so just from very dimensional analysis kind of arguments that we did in the 4th lecture, we know that the answer to this has to have units of 1 over GeV squared, right? Because 1 over GeV has units of length, and so there's the only thing around that has the relevant units is the mass of this thing, and so just from these very simple arguments to within factors of 10 or so, this cross section has to look like 1 over the mass of the W Z squared, and we also know from these stick figures that there's a coupling value here, right? There's this value that controls how probable this interaction is. And this is the right answer. So this is the answer you would just guess from naive dimensional analysis. If you did the full calculation, there's a 2 pi or something that shows up there. But this is essentially the right answer. And now we can put in, again, to get a rough estimate. This value, this weak coupling is like 1 over 50, we saw before, and the mass of these things is like 100 GeV. And so you can put those in our GeV units, you get that. And so this comes out to about 2 per million. And we talked about that the cross-section for just protons to interact, or how often the area for this to interact is like a GeV, GeV to the minus 2. And so the ratio of these tells you how often you're producing a W. So the ratio of these is like 1 in a million. And so this means that for every million proton collisions, we produce one of these WZ events. Okay, so now we'll do the exact same thing for the Higgs. Again, this is getting a rough feel for how much data we'll need. So it's the exact same thing, right? But now the diagram is a little different. But again, the area, the units here are area, and the only scale in the problem is the mass of the Higgs. But now we have these other vertices that we have to account for, and we have this fact that there's a loop here. Okay, and so that's exactly what's shown here. This is the loop factor that we talked about in the 3rd lecture. We have 2 of these strong, these alpha strong. These are couplings that are to the gluons, and then there's a weak coupling that's there. And then you have the mass of the Higgs itself. And the mass of the Higgs, we're looking for something like 100 GeV. And so we can put in all these numbers. It's the exact same thing that we just did. Now there's more of them. And so now if you work this out, you get 1 times 10 to the minus 10. So 1 in like 10 billion. Okay, but so if you actually work it out, there's another factor of 10 that shows up in this squiggle. And so you really get 1 Higgs per every billion proton collisions. Okay, so it's 1,000 times rarer than the W and the Z, even though you're looking for roughly the same mass. Okay, so that's how often we produce Higgs. Now, how much data do we want to produce? Okay, so a good target is about 100 Higgses in the way that we could see it. Okay, so like 100 Higgs events in gamma gamma. 100 of those gamma gamma pictures. This is this is a rough target. It's good because 10 is probably too little. You couldn't really study it if you could probably make a discovery with 10, but you couldn't really study its properties. So this is a target that was used when designing the LHC. Okay, in a year, let's see. So if you want to produce 100 Higgs to gamma gamma in a year, that means you have to produce 10 to the 5 Higgses, because there's less than a % chance that the Higgs will decay in this way. So that means we need about 10 to the 5 Higgses per year. And a year is about 10 to the 7 seconds. Okay, so this is how many Higgses we have to produce per second. And now I put in this little epsilon factor here, and this accounts for the fact that we don't run the LHC all year. We also, when we are running it, it's not active the whole time. And then there's also inefficiencies with the detector and processing the images, and a whole host of things. So we don't see every single Higgs. We're not recording Higgses every single second. And so roughly this number is about 1%. And so about 1% of the year that we're really running and recording data that's viable. And so if you put in a % here, that means you're going to have to produce 1 Higgs per second. Okay? If you want to get 100 Higgs to gamma gamma per year, you need to produce 100 Higgs, or 1 Higgs every second. Okay, so this is the goal of the LHC. And so, but that, we only produce 1 Higgs for billion proton collisions. So now this is saying that we have to produce 1 billion proton collisions per second. Okay, which is, this is, a big cost driver of everything involved. Now we also have another problem here. As I mentioned last week, these beams only collide 40 million times per second, right? So they're not colliding 1 billion times per second. So in order to get 1 billion proton collisions from 40 million beam collisions, we need 25 collisions per crossing. Okay, so it's not enough that we're colliding at this very high rate. We also have to have many proton collisions each time they collide. Okay, so there were some questions last week about, we can't, of course, we can't even save all these 40 million events. So why don't you reduce the, a good thing you might, a thing you might think is, why don't you reduce this number so you can save all the collisions? But you can see if this is the target, reducing this number would increase the number of protons that we would have to collide every time there's a beam crossing. Okay, and so I just want to say that this is actually a big challenge for the experiments. This is also a cost driver, one of the reasons these things are so expensive. And so I'll try to just motivate that very briefly. So this is one of the pictures that we would look at that would be like a Higgs decay. So one of the ways that the Higgs can decay is to pairs of Z quarks, so Z bosons, not Z quarks, Z bosons. Those can then decay to leptons. So you'd have four leptons. So here this is like an electron. This green thing, here's another electron, and then you have these red things are muons. Okay, so this is the type of picture that we looked at last week. Here's sort of another drawing of it. This is now, this is the same event, but it's in it's looking at different dimensions. So this is now looking along the beam pipe. So in these pictures, the beams are really going into and out of the screen. Here the beams are coming in, they're going in this way. So this is really the image that we're looking for. This is the one that would tell us that there's a Higgs boson decaying in this way. But we have to have 25 collisions per crossing. So really these images don't look like this, they look like this. Okay? And so you can see that there's the collision that we're interested in, but there's also these 25 other collisions that we need to just get enough data. And they make and you could, you imagine processing this image is much more difficult than processing that image. And this is another big challenge with in this business, is dealing with images that really have a lot of noise from these other collisions that we're not interested in, and being able to process all this information in real time is a challenge. Okay, so now I'll move. So now we know sort of how much data we need. We know how to look, where to look. etc. Now I'll talk about what was actually done. So we use these three. This will be relatively brief because I think you may have seen it before. But so we're going to study these three basic channels. The first one is that we'll talk about is the case of two photons. And so here what we're looking at is pictures that have two of these things. A photon will look like a cluster in the electromagnetic calorimeter, okay, that doesn't have a track associated with it. Right? If this was an electron, there would be a charged particle trajectory pointing at it. But we're looking for photons, so there should be events that have two of these. And so here's an image that looks just like that. So you have a bunch of stuff that's happening mainly from the other protons, or the other collisions that we just talked about. But there's also these two clusters of energy in the calorimeter with nothing, without charged particles associated with them. Okay, so this is a sign that you have a photon, and there's two of them in the event. So we process all the images that we can, and we select events that look like this. Okay. Now, of course, just because you see a picture that looks like this doesn't mean that was from a result of the Higgs decay. There's a lot of other ways you can produce pairs of photons that aren't related to the Higgs, and this is something that's known as a background that we have to account for. And you can see that in this plot here. So what this is showing is the mass of the two photons. Okay, so basically adding up their energies and calculating what the mass should be. And then what you see is as a function of the mass for all the different pictures that we see, how many pictures do we see, essentially. Okay, so you can see that it's this distribution that's falling, so we're seeing less and less pictures as you go to higher masses. And the background that we expect from things that are not due to the Higgs is relatively smooth. So it's smoothly falling, and it's no real features in it. That's something we're able to predict roughly from the theory, and we're also able to constrain using directly the data. And so in fact, what you see here is the data, that's what's shown in black, these black points. Then there's our estimate of the background is in this is in this dashed blue line. So the background fits well up here, it goes down, and it's very smooth here. And you'll notice that there is a feature in the data that's not predicted in this background, and there's a little bump here. Okay, and if you take the data in black minus our background fit, okay, you get what's shown at the bottom. This is sort of the excess over what we expect just from background. And there's a bump here, okay, and this is what you would expect if there was a new particle, and it has roughly the energy or roughly the mass that we were looking for. Right? We were looking for somewhere between 115 and 150, and that's what's seen. Okay, so that's one way to do it. Another way that the Higgs can decay is to pairs of Z bosons. Okay, and then the way we see Z bosons is their decays to leptons. So in particular, they can decay to 4 electrons. Okay, they can also decay to 4 muons. They can decay to muons and electrons, also taus. But this is one of the ways, and you see a picture that is consistent with this type of decay here. So what you're seeing here is clusters of energy in the electromagnetic calorimeter. That's this green thing. So you see 4 of them that are relatively large, with very little energy behind it in the hadronic calorimeter. So this is a good sign that there is either an electron or a photon in the event. It's hard to see here, but there's these very straight red lines that are pointing exactly to these clusters, of course. But also the images is 3-dimensional, right? So you can also you can see if it's consistent in the other dimension that I'm not showing here, and in fact they are. Okay, so this is a sign that you have an event like this. And just with the photons, just because you see an image like this, doesn't mean that is the Higgs boson that you're seeing. It could be due to other related or other unrelated processes. And so we have to account for that. So that's what you see here. So here there's a lot fewer events. This is a rarer process. So what you're seeing again is the data. So this is the sort of the number of pictures that we observed as a function of the mass of all the energy of the 4 objects. Okay, and then you can see there's a number of ways you can get pictures that look like this. So you can produce just Z bosons directly, so without the Higgs. And that looks like this red distribution. Okay, so this is something that we can predict from the theory itself. And there's other ways too. There's, these are a bit smaller. I won't talk about them, but we can also predict what they are. And so what we expect without the Higgs, with no Higgs boson, you would expect the sum of this red and purple. Okay? And what we actually observe is an excess. It's noisier because there's less data, but there's an excess of events observed here over what we would predict that again is roughly in this region that we would look at. Okay, then the third way that we look for the Higgs is it's the case that the W's, it's a similar thing. This is actually the channel that I worked on. It's a lot harder because you have these neutrinos that we don't observe. So we really see, there's two of them. So we actually look for pairs of electrons plus momentum imbalance, which is the sign of one or many neutrinos. And so you get pictures that look like this. So again, we have things that look like two electrons in the event, in this case, and then there's a big, if we would sum up all this energy, there would be a big imbalance, or we say missing energy in this direction, and that's indicative of there being some neutrinos in the event. And so here we select images, it's the same game. We select images like this, just because you see one doesn't mean it's from the Higgs, so you have to estimate the backgrounds. This is a much harder way to do it because you don't have all the degrees of freedom, right? Because there's these two neutrinos that you don't see, you can't make the full mass of the system. And so what we use is some estimate of the mass by using the information that's visible to us. So it's a much coarser variable to use. But that's what you see here. This is again plotted as a number of pictures versus this mass. And so this isn't expected to peak exactly where the Higgs is. It's expected to peak a little bit below the Higgs. And again, you can see there's contributions from other processes that aren't the Higgs. So in particular, there's just regular production of W's. Looks, of course, just like a Higgs decaying to WW. And so anyways, we can estimate that using a combination of measurements and data and from theory, and this is we would predict a value that looks like this. Okay, so the sum of these up to this purple distribution. And if there was a signal, okay, we would expect to see an excess that's shown in red. So above what we see in this purple color. And in fact, what we see in data is even a bigger excess. Okay, so we see more events than is predicted by background, and also there's more events that's predicted by just the Higgs signal here. Okay, so from all of these, we're seeing an excess. The excess is also consistent roughly in where the mass is observed to be. And so this is really a good sign that we're seeing something that's actually consistent. This is a plot that was shown in the news a lot. You'll see it even on T-shirts. This is basically trying to estimate, how confident are we that there's a new particle here? Okay, and what this shows is the probability that these excesses that we're seeing is just due to a fluctuation in the background, and that there is no Higgs particle as a function of the mass that we're looking at. Okay, and it's a little complicated here. So let's focus on this blue thing first. So this thing is showing what you would expect to see if there was a Higgs at a particular mass. So if there was a Higgs sort of at 115, you would expect to see an excess, of course. And if you ask this question, how probable is this excess with background, just being a background fluctuation, it would be about 1%. Okay, and if the Higgs is heavier, it's easier to see. It looks less like background. And so if it was at 135 GeV, you would expect to see an excess again. If you asked how significant this excess is, or how likely is it to be from background, it would be a number that was like 10 to the minus 9, so 1 in a billion. Okay, so this is what we expect. Okay, and there's uncertainties, of course, due to statistics and other errors, and that's represented by this blue band. Okay, so it should be, this probability should be between 1 billion and up here, so 10 billion or so. And then what we actually observe is the solid black line. So that's this curve. And you see that for lower values of the Higgs mass, what we see is totally consistent with background. Right? The probability that the events that we see are background is like 50% or something very high. And that's the same thing at high masses. So here, it's like 50%. Or if there was a Higgs, we would expect to see, disagreements at 10 to the minus 11. But in this region, we do see an excess, as we just saw in the last 3 slides. In this excess, the probability that this is just due to the background fluctuation is about 1 per billion. Okay, so that's evidence enough for me to think that we're not seeing just a background fluctuation. And not only do we see something that's very significant, it's roughly compatible with what we would expect naively if there was a Higgs. So this is very close to within this band. Okay, so this is something that convinced a lot of people. It's a very formal, the people that do this tend to be very serious, almost like statisticians. The thing that really convinced me was this plot. So what this shows is the signal strength, okay? And signal strength is just the cross-section that we measure divided by the expected cross-section. Okay, so if it was just the standard model, it was exactly the standard model of Higgs, you'd expect this number to be 1, so that would be along this line here. This is shown as a function of the mass. So basically, the probabilities that are extracted for the Higgs to be produced as a function of its mass. And you can see the measured values for these different channels. So the red is for the pictures that look like 2 photons. Then you have the blue is for the ZZ decays, and the green is for the WW. And so we saw that they all see an excess, but that excess is all roughly at the same masses. Okay, so these guys have pretty good mass resolution. What they're seeing is consistent both in terms of the mass that they see and in terms of the rate. Okay, so they're seeing roughly the same excess that you would expect from a Higgs at the exact same mass. And the same with WW. So it doesn't have as good mass resolution because of these neutrinos, but it also sees an excess that again is consistent with both the rate that is predicted by the probability to produce the Higgs and the mass. Okay, so this really convinced me that these 3 things that are looking at very different pictures, they have very different backgrounds, they nonetheless converge to the same picture. Okay, so really I think this was a triumph of humanity. Okay? And I don't think we really stressed how great an achievement this was. This is something that had been predicted in the 60s, and it was really forced on us by principles that were discovered much before that, right? That was the whole point of the first half of this lecture series. And so, the fact that if you take those seriously, it predicts these very esoteric things, right? The number of photon events, or the number of photon pictures, number of these pictures, that you can essentially predict that 60 years ago, if you build this, you go to all this trouble about building this big collider, you spend billions of dollars, you would expect to see a signal that just exactly has these properties, and then of course we do that, right? And the fact that we're even able to test this in this way is also, I think it's a triumph of humanity, right? We're building these huge detectors and colliders. We're able to process the data that's enormous volumes. Of course, there's a whole bunch of machinery that I didn't talk about here that is behind all this, right? We have to measure how often things are in a proton. That is all come from measurements. So it's really, sort of, you can think of it, it's certainly at least a 20-year enterprise, but really, it's almost a century in the making. Okay, so I think this doesn't get stressed enough, but yeah, of course I'm biased, but I think this is really one of the best things that we've done. Okay, so now this was all a few years ago. I want to talk now about what we're doing with the Higgs post-discovery. So what do we know now, and sort of where are we going in terms of studying the Higgs? Okay, and so just for the current status, so this was this photon measurement that we looked at before. This is what it looks like now. Okay, it's still there. We're able to make this fitting more finer, and we continue to see this excess. Here is CZ before. Here it kind of looked a little dubious, right? There was, it's not that significant here. There's also excesses up here. So this is what this looks like now. So this really has gotten a lot better. So now this, we really worked hard to make these peaks bigger by accepting more events and taking better pictures. And so now you can see we really have a big excess in this region. Right? So this is what the ZZ looks like. Here's the WW. So this also kind of looked a little fishy, right? You saw an excess, but it was even bigger than what you'd expect from just from the signal alone. This is now what this looks like. So we've added a lot more data here, so it's almost 10 times the data here, and now it looks much closer to what you would expect. Okay, so in fact, this is the difference. This is the difference in just the background. Okay, that doesn't have the Higgs from the data. You see this excess here, and then the red is showing what you would expect from the Higgs. So now it's also much more consistent. And these improvements are mainly because we've doubled the amount of data since its discovery. And we've also been able to specialize the analyses now that we know where to look. So now that we know in detail where the Higgs mass is, we can dedicate more resources to saving those particular types of pictures. Okay, so what's the program? What's really the program beyond the discovery? So there's really 4 main points here. The first is to establish signals in the harder channels, so the ones that were more difficult to see. This has been done in the tau decays, okay, that we talked about, that weren't useful for discovery. There's also a big program to see direct Higgs to top interactions. So remember that the Higgs actually has a very small probability to decay to tops, so you have to see this interaction when you produce the Higgs. It's much more challenging, but we're actually close on this. And we're getting close also in the most common decay mode, this Higgs to BB. That's what it does 60% of the time. That's really challenging because of the amount of backgrounds. But we're getting close to being able to make a significant observation in that channel. Okay, so we want to find these. This is really still discovery mode for these different processes. For the signals that we've already established, we want to compare the measured and predicted interaction strengths. Right? So how often what's the probability that we produce the Higgs? Is it consistent with what we expect? And is the way that the Higgs decay consistent with what we expect? Of course, we have this new particle. We can measure its spin, and we have an expectation for that, what that should be. And then we also, because we know that there's a new particle, we want to look for unpredicted decay. So maybe there are ways that it can decay that we weren't expecting that are easy to see. And so there's a whole program looking for that as well. So I'll just run through some of these results here. So this is looking at the production cross-section, the probability to produce the Higgs. And what you're seeing here is the measured probability. This is in terms of the signal strength again. So it's sort of how different it is from what you would expect. And you see there's two axes. This axis is really showing this process where you produce the Higgs from the W. And this is showing the probability to produce the Higgs through this gluon fusion through TOPS. And then you see the measurements in these different channels. Okay, so the photon Z, the W, here's the tau measurement that we didn't talk about, and there's even a weak measurement from the dB. So each of these gives a region in this plane, and that region is shown here, okay, with the different colors. And the first thing to note is that they all overlap. Okay, so that means that they're all seeing excesses that are consistent with one another. And in fact, they all overlap in the point that's consistent with the standard model. Okay, so this just simple Higgs version predicts both of these things to be 1, and that's exactly where the overlap region is. So the rate at which we're producing the Higgs is consistent with what we expect in all these different channels. We can also look at try to measure the interaction strengths directly. Okay, and of course, we've seen this a million times. It depends on the mass. And here's what we observe. So this is showing the different particle masses, and this is the interaction strength that is inferred from the measurements. And you see the prediction is that this should be this linear dependence, and that's exactly what we observe in these channels. So, so this top interaction is inferred from the loops. Looking at what that interaction strength must be based on the production cross sections. The W and the Z we're able to measure directly. I mentioned that the tau we can now see, and we have this is just a limit on the mu on 1, but we know that the mu on 1 can't be up here, so it has to be here. So again, this picture is consistent with what we expect from these types of diagrams. And now I'll talk about spin. So we expected it to be a spin 0 particle, but there was the spin 1 wasn't excluded, right? It could have been a spin 1. But if it was a spin 1, we would be in this trouble that we would need another condensate to explain how this thing has a mass. And so that was sort of a strike against it being a spin 1. But now the fact that we see it decaying to photons rules out a spin 1. So if you have a massive particle that is spin 1, it cannot decay to photons. And this is from these basic principles. So the fact that we see a significant signal here excludes spin 1 directly. And so now we know it has to be a boson because it couples to matter. Spin 2, we also said it probably wasn't spin 2 because doesn't decay like, or it doesn't act like a graviton. But we can actually also use the data to see if that's borne out. And so the way that we can tell whether or not it's spin 0 or spin 2 is by studying the angles in the pictures. Okay, so in particular, if we think about like the Higgs decaying to WW decays to 2 leptons, we look at pictures that look like the ones we saw before, where you have 2 leptons and a big energy imbalance. Now, if it's spin 0, you expect most of the time to look like this, to have the angle between these two leptons to be relatively small. If it's spin 2, on the other hand, you would expect on average this angle would be much bigger. Okay, and that's what you see here. So this is just showing, this is not a prediction from the theory if you would have a spin 0 versus a spin 2. This is sort of the number of events you would expect, or the number of pictures that you would get as a function of the angle. Okay, as a function of this angular distance between the two. And so what I said was if it was spin 0 or something that's like a Higgs, you'd expect to see more often events that look like this. And if it's spin 2, more often you would expect to see things that look like that. Okay, and so you can do this directly in WW. You can also do this in ZZ. ZZ is actually a little bit better to do because you have more information. You can measure all the decay products. And the photons also can tell the difference. And so, again, this is a really a formal plot that uses a lot of statistics. But basically, what you should think is, if you have a spin, if it's spin 2, okay, if it was really the thing that we're measuring is spin 2, the distribution of expected data, our data should look something like this red plot. Okay, it should lie somewhere that's roughly consistent with that distribution. If it's spin 0, it should look more like the blue plot. Okay, so if we had the same data set over and over again, it would be drawn somewhere from either the red or the blue. And the actual data that we observe is this black line here. Okay, and you can see that that is much more consistent with coming from the blue data than that would be from coming from the red data. And so we say that this, and so you can translate this basic picture into statistical arguments. But I don't think that's so interesting. But you can see it's clearly favoring spin 0. Okay, so another thing that we can do is test compatibility of the Higgs couplings. Okay, so now of course we can't do as much as we'd like here because we're limited by statistics. So what we tend to do is we sort of do different scenarios. Okay, so example is we say that we'll allow this coupling to change. Okay, and so we'll put in some new what we call a coupling modifier. So some new parameter kappa. Okay, that is 1 in the standard model, and if it's and maybe it's not, maybe our data is telling us that it's not 1. So here's another. So we could do that for the W and the Z. We can ask to see if this, how different could that coupling be, and we could do the same thing in different ways. So here's a case where we put in a coupling modifier for the fermions for the top quark, and we put in a coupling modifier directly for the gluon. Right? So you can either think of it this, you can either say maybe there's a whole new particle here that's interacting with the Higgs, or maybe it's just this modifier. And so we basically build different benchmark scenarios, and it'll be clear when I show this in the next slides. So this first example is testing for differences in fermion and boson couplings. Okay, so basically you assume that the W and the Z, whatever modifier they have, is the same. Okay, and we can actually test that this is true with our data. And so you put in coupling modifiers that would, this kappa V that would multiply this interaction, and then a separate fermion multiplier that would modify this interaction. Okay, and then for the gamma decays, there's 2 of them. So this can actually be a top quark just like in the production mode, and it could also be a W boson. Okay, and here you also assume that there's no unknown particles in the Higgs. Okay, so if you make these assumptions, then you can test, you can measure how different these kappas are, and that's what's shown here. And so again, we can measure this in all the different channels that we see, and that's what's shown by these shapes. The standard model is, of course, no modifier, so just one, and all these shapes again overlap, and they're consistent with this picture that there's no significant modifier to the coupling. So that was one scenario that we tested. Here's another scenario. This is saying that we'll just, instead of in detail saying that, yeah, there is a loop here and I'll just modify that coupling, you say maybe there's not even a loop to begin with, so I'll just put an effective coupling modifier that modifies this gluon interaction. And the same for the photon, right? That's also a loop. So I'll put in these modifiers, then I'll assume that the fermion and the boson modifiers are 1, so I'll fix those to 1, and I'll assume that there's no new particles. Okay, so if you do that, we can then test for what these look like, and that's shown here. So here what you see is with the coupling modifier for the photon loop, and here's the gluon loop. Of course, standard model is 1, 1. And here you see measurements from Atlas. This is the experiment that we talked about yesterday. There's another competing experiment, CMS, that's very similar, and they also make this measurement in red. They overlap. It's 1, 1. If you do a statistical combination, you see something again that's very consistent with being 1. Okay, here's another case. Now we'll keep these same modifiers, and we'll now allow the case unknown particle. So now we'll say that maybe there's some new particle that we don't know about that's the Higgs is decaying into, and you can interpret the data in this form. And so this allows us to measure or to constrain what these modifiers are and how often Higgs is decaying to a new particle. And this is interesting, as we'll see next week. You might think that the Higgs is decaying to new particles, and what's shown here is how often, or the branching ratio that the Higgs is decaying to something new or unknown particle, really. And this is our best fit of this, and this is like the likelihood, and so it wants to be above. This upper limit is what we use to say that this space is ruled out. Don't worry in detail about what this means, but basically, this is saying that the Higgs decaying to unknown particles has to be less than like 35%. Okay, so that's a big constraint on what the Higgs might be doing. Okay, so now what don't we know? So I told all these things about what we know. Okay, so we don't know if these established couplings are modified at 20% level. So if you go back and look in detail at those figures, there's room for the overlap to be different from 1 to within about 20%. So it could very well be that there are coupling modifiers where the coupling doesn't go like the mass, and it has 20% deviations. So that's still allowed. The Higgs can also decay in an unexpected way, so to either new particles, if the particles we're not expecting, 30% of the time. That's still allowed. There's also a lot of unobserved interactions. Okay, so we've only seen the Higgs decaying directly in a very few number of ways. And so these red guys are essentially all unobserved. I put a dashed circle here. We haven't directly observed the Higgs interacting with either the top or the bottom, but we have strong evidence that that's happening, just from the consistency of the overall picture. Okay, and there's another very important one that I haven't talked about here. The Higgs can also interact with itself, right? I mean, the Higgs is a boson. It's a particle that should now be on our list of all particles in the standard model. And in fact, there are predicted interactions that look like this. Right? These again are allowed by our basic principles. So we can have 3 bosons interacting once or 4 interacting once. And this is something that hasn't been observed. And I think maybe I'll end here. I can talk about why. So these interactions are actually really important. Maybe I'll just end with this. I'll go through this next time. But this Higgs self-interaction leads to di-Higgs events. So events where we produce 2 Higgs bosons at the same time. And this is really, in many ways, the ultimate goal in the Higgs program is to measure these di-Higgs events. Okay, this allows us to directly probe this Higgs field potential that we put in, and it has deep connections with the fundamental problems with the standard model that I'll talk about next week. And so I'll pick up here next time. Maybe take a few questions.
When you mentioned that it became other unknown, does that include other?
Right. So the question was when I was talking about when the Higgs indicated other unknown particles, does that include other Higgs bosons? Yes, so that includes everything. It can include things that are within the standard model that we just haven't looked for. So maybe it can indicate up quarks with very high probability. So it includes things like that. It also includes the case that we can't observe. So maybe it's decaying particles that we just can't detect in our detector that will make no images, and that's also included in that study.
It's my understanding that the Tevatron at Fermilab actually saw that data bump first and gave the information to CERN. But anyway, can you just make a comment about what contribution the Tevatron may have made?
Right. So the Tevatron was looking for the Higgs. They actually had an exclusion. So it was. So when I went through this argument of where to look, I said it has to be above 115 from experiments at these precursors of this electron collider. There was also a search at the Tevatron that also excluded a region at the higher end. So it excluded around like 160 GeV that was looking for decay W particles. And then very shortly after the Higgs discovery was announced, the Tevatron did an analysis looking for Higgs decaying with pairs of deep quarks. And there they had a significance that was like 3 sigma. So they sort of had evidence for it. I think if you just saw that analysis, it would be very hard to swallow that it was the Higgs boson, because they saw an excess over a lot of background. There was no corroborating evidence for it. But in retrospect, it does look like that they're seeing some evidence for Higgs decays, and there's that.
So in 2012, when all this popped out, I assume you were at the very center of it, right?
Yeah.
So I'm wondering what went on in terms of interaction between, let me back up. Did CMS see it at the same time you people did, the Atlas group did, and how did that go about the whispering that went on before the news broke out?
Right, yeah, so there were these two teams that were looking for it. And yeah, they both saw very significant results. They were different. The Atlas ones, if you go back and look at the handout, the excess seems even bigger than you would naively expect. Okay, and so that means we were able to say that we're seeing something with higher significance or higher confidence. But I think there's no indication that that was anything but fluctuation. And so Atlas did have a slightly stronger signal, or appeared to be stronger signal, but it wasn't inconsistent with what CMS saw. They were also roughly at the same time. I mean, there was, so the thing is, these, of course, a huge fraction of the collaboration is working on this because it's a very well-defined thing. It's the obvious thing to look at. And so these things really came out as soon as possible. So both experiments are on a very similar time scale because they have similar difficulties in processing the data, et cetera. That's stuff that's, time scales of that are limited by computing resources and things, and they're very similar to the experiments. So these came out really basically simultaneously. Another thing is, of course, there are rumors. Once the data is processed, the experiments know the answer before they tell the world. But there really wasn't that much. It's been. I think you get a lot more rumors if you find something that's new and something that really doesn't look like what you expect. And that really wasn't the case here. So for the Higgs, there wasn't that much rumor of before the actual announcements. It was also true that the announcement happened very, very quickly after we internally knew the answers to the analysis. So there wasn't much time for rumors to come out either. But that's definitely a problem going forward. Looking, if there's an excess in one experiment, often it gets leaked to the other experiment, and now that could potentially bias what they're looking at.
You said you were going to answer this later. I don't know if this is time. At what level, theoretically, should we not build cyclotron because of
That's next lecture. So the question was, at what level should we not build cyclotron? And we'll talk about that next week.
100 tens or something?
Well, I'll give a very precise answer to that next week.
Yeah, I wonder how all these understandings help us to understand the biological or how life was potentially derived for all these interactions.
Right. So the question is, how does this help biology? And so it doesn't really. I mean, it depends on how philosophical you want to be, right? I mean, we saw that the Higgs coupling to electrons directly determines the size of things in the universe. Right? So the size of life is you could take the viewpoint that the size of life is critically dependent on the Higgs coupling to the electron. If the Higgs coupling to the electron was, 100 times different, life wouldn't exist, basically. Right? And so you could say that there's this immediate connection, direct connection. Now, of course, we knew what the electron mass was before we discovered the Higgs. So if we couldn't, it's not like we could discover the Higgs and learn something about biology. But it's true that ultimately these things in biology are directly related to properties of the Higgs. And now we really have now we can really answer the question why. We have a more in-depth answer of why the electron has the mass that it does. So before we couldn't say, so you can ask, well, why is there life, right? And that question would ultimately go down to there can be life because the electron mass is such that it could allow it to exist. Then you could ask, well, why is the electron mass such that it's in this range? And before we had no reason for that, right? We would just say, well, the electron has a mass. But now we have a more refined understanding of why the electron has a mass. It has a mass because it couples to this Higgs field. This Higgs boson is a direct confirmation that this Higgs field idea is right. So it's not like learning. It's not like measurements of the Higgs boson will tell us about biological, workings of biology. But it really completes the overall picture, and it allows us to answer. It's probing science at a deep level. Is everyone happy with that answer?
Is anybody working on the problems of inertia, or are they not for two reasons? One, they want to completely work out the Higgs problem to its nth degree, and two, it's because we don't even know where to start.
So what's the problem of inertia?
What causes inertia? What causes resistance, change of motion, and blah, blah, blah?
Yeah, so I think people certainly aren't working on that. I think it's because it's just an outcome of the theory, right? It's a consequence of the basic interactions. So you can ask why there is, why quantum mechanics is the way it is. If you change quantum mechanics, you would change the relationship of mass to what a force is. There are people that are thinking about ways to extend our notion of quantum mechanics, but they're not they're not concerned with these much higher level things like inertia and forces, right? And that's really a very derived consequence. Right? We think at the fundamental level, it's only these stick figure diagrams, and if you sum over a lot of those stick figure diagrams, you'll get forces, and those forces behave in a way that's very similar to, or that it gives you F equals ma to a very high accuracy. But I think there's no deep reason why F equals ma, other than that's a consequence of these basic stick figure diagrams. Okay, so next week we'll essentially everything I've talked about so far has been really solid. There's no disagreement within the field on this. Next week we'll switch into less certain territory. I'll talk about problems with the standard model, so things that everyone agrees that are big issues, and then I'll give some indications for what can solve those. And there's not agreement. Okay, so there I will sort of present the way that I think of it, but that's not exactly. It doesn't mean that that's the way that it is.